Okay, in this video we're going to look at making the binomial model, but for starting off we're going to using the binomial theorem expand p plus q to the power 6. Use this to explain the binomial distribution for probabilities. Okay, so using the binomial theorem to expand p plus q to the 6 in ascending powers of p, you would have done this in your pure mathematics course. So p plus q to the 6, using the binomial theorem, is going to be q to the 6 plus n 6c1, p to the 1, q to the 5, we don't write the 1 in though, plus 6c2, p squared, q to the 4. Maybe pause the video and see if you can write down the remaining terms for yourself. Did you come up with 6c3, p cubed, q cubed, 6c4, p to the 4, q squared, plus 6c5 p to the 5q plus p to the 6. Now you should know that nc6 is n factorial over n minus x factorial or x factorial. Now if you want to use this for probabilities, in the binomial model, p plus q, remember, is equal to 1. Remember we calculated q by doing 1 minus p. Remember, p was the probability of success, q was the probability of failure. So, and we can, if we've got a discrete random variable, we can put them into a table like this. It's discrete because x can only take on exact values. So going back to this example, where x was binomially distributed with n being 6, and the probability of success being a quarter, then n is the number of independent trials, 6 in this example. P is the probability of success, 1/4. Q will be the probability of failure or not success, which is 1 minus P is equal to 1 minus 1/4 is equal to 3/4. In the previous video, I used P as being probability of getting a head on a biased coin, and therefore Q would be the probability of getting a tail. So we've got two outcomes, success and failure. So if we want the probability of no heads, or not P, that's going to be 3/4 to the power of 6. We don't need to put any combinations in because they would just be equal to 1. So we'll put 3/4 to the power of 6. If we want the probability of x being equal to 1, then we consider this one. So it's 6c1, 1/4, 3/4 to the power of 5. X being equal to 2, we consider this one. 6c2, 1/4 squared, or 3/4 to the power of 4. Next one, we will consider this one. 6c3, 1/4 cubed, or 3/4 cubed. And the next one, we consider this. Goes into here. 6c4, 1/4 to the 4, 3/4 squared. And for 5, we consider this one. 6c5, 1/4 to the 5, 3/4, and then 1/4 to the 6. What you should notice is that the power, if you add powers, if you add them together, are always equal to 6. And whatever goes here is the power of what goes here. 2, 3 cubed, 4 to the power of 4, 5 to the power of 5. If we work these out, you can work this out using a calculator. 729 over 4096, 1458 over 4098, 1215 over 4096, 540 over 4096. I haven't cancelled any of these down. 135 over 4096, 18 over 4096, and 1 over 4096. The good thing is, if you add these together, of course, if p plus q is 1, 1 to the 6 is 1, then all of this must also be equal to 1. So if you sum all these probabilities, you will get 1. Okay, so you can use this binomial theorem to come up with probabilities, provided that the sum of here is equal to 1, and we need to have n independent trials. two outcomes, a success and a failure, with the same probability each time you do the trial. So P is a quarter and then Q is 3/4 in this case. So if we want to find something like the probability x is greater than 2, then from the table that's equal. It's easy because we would just have to sum all these probabilities. That's this one plus this one plus this one plus this one. It's quite easy if they're all over the same denominator. Gives you 1909 over 4096. But can you find an easier way of doing it? Well, yes, because we can say the probability that x is greater or equal to 2 is 1 minus the probability is equal to 0 minus the probability is equal to 1, because all these probabilities add up to 1. So if we subtract those from 1, we will get that number. For something like the probability that x is between 1 but less than 4, then you have to consider the probability that x is equal to 1, probability that x is equal to 2, probability that x is equal to 3. So you're adding up probabilities. So you've got from here to here. We don't include 4 because it's not equal to 4, but we include 1 because it's equal to 1. We get 3,213 over 4,096 if we add these three probabilities together. So, in conclusion, the conditions for a binomial model are 1. An experiment that has a fixed number of independent trials, i.e. n was 6 in my example, and there are two outcomes: success, always with the same probability of p, which was 1/4 in my example, and a failure with a probability of 1 minus p, which was equal to q. If these conditions are met, then we have a binomial distribution. This is a discrete distribution and can only take on exact values. In our example, we had x equal to 1, 0, 1, 2, 3, 4, 5 and 6. We say that x is binomially distributed. We have two parameters, n the number of independent trials and p the probability of success. And we can find the probability of x being equal to some number, one of these in our example, by doing NCx, p to the x, q to the m minus x. Notice if you add these together, x plus n minus x, you get n. Alright, so n goes with this number here, x will go with the p here, where q is equal to 1 minus p. These are called the parameters of the distribution. So most distributions have parameters. The binomial distribution has two: n, the number of independent trials, and p, the probability of success. You can find q from that, and x is normally given in the question. Okay, this has been a video to show you about the conditions for a binomial model and how we can come up with binomial probabilities. I hope you understand, and I thank you very much for watching.